Okay, so what we're going to be looking at is something called rational functions in this section. And so rational functions are a certain type of function that actually has two polynomials that are being divided by each other. So it's a polynomial divided by another polynomial. Or if we were to write it in more of a general sense, f of x is equal to p, capital P, polynomial x, all over qx. Okay. Now, with these rational functions, what ends up happening is that sometimes we do not have a domain that includes all real numbers. Okay, so there are certain numbers that will not work in this function. If we were to plug it in, it doesn't exist. So in this case, whenever we want to search for what is our domain, we assume that it's all real numbers except for where the bottom, qx, equals 0. If it equals 0, we have no answer. Okay, we either have what's called a vertical asymptote, or we have what's called a hole at that location. Okay, and so that's what we're going to be looking at specifically, and looking at, okay, where's the domain and range? And to find that, we just zero out the bottom. So we set the bottom equal to 0 and solve those for x. So let's say we want to find the domain of each of these. Okay, and remember, the domain is the x values. So for these, we're just going to look at the bottom. So x squared plus 1, we're going to set it equal to 0, and then solve for x squared, or solve for x. So we get x squared is equal to negative 1. Well, when we take the square root, we can't take the square root of a negative 1. It's I. Since that's not a real number, we would say that it would be all reals would be in our domain, because we have no real number that zeroes out the bottom. Okay, because this gets us an I, which we don't worry about because that's not real. Okay, so now let's look at the next one. We're going to take x squared minus 4, set it equal to 0, solve for x. X squared is equal to 4 by adding it to the other side, and then taking the square root of both sides, giving us an x equals plus or minus 2. And so that would be where we do not have our answer. So we would say all reals except for when x equals plus or minus 2. Okay, because that's where it zeroes out the denominator, and wherever it zeroes out the denominator, it does not exist. Okay, so now if we look at the last one, that one's pretty simple. We take, again, the bottom, and we set it equal to 0. So x plus 1 is equal to 0. Solve for x gets us x is equal to negative 1, which means we get all reals except for when x is equal to negative 1. And that would be our domain. Okay, so again, it's all reals except where the bottom equals 0. Okay, because we can't divide something by 0, because you can't put something into nothing. And if you divide by 0, the whole world implodes on itself. But all right, now this point where this occurs, where the denominator of a fraction equals 0, of a rational function equals 0, these are called points of discontinuity. Okay. Now, points of discontinuity are basically where you have breaks in your graph. There are two different types. There's a vertical asymptote, which I kind of mentioned earlier, and there's a hole. A vertical asymptote is if you zero at the bottom, and when you plug that number back into the original, or into the top, it does not zero it out. So if you were to plug in a number and you end up getting 3 over 0, that is a vertical asymptote. And what a vertical asymptote is it's this imaginary line, which is this purple line right here, where your graph won't touch it, it won't cross it. Okay, it'll just skip over it. Okay, and it's an imaginary line. A hole, on the other hand, is if you find a 0 in the denominator, and when you plug it into px, you also get a 0. So if you get a 0 on the top and the bottom, or if it can be factored out, that is where you have a hole. And a hole just looks like that. The graph continues, but then you just put a little hole in it. You just have a spot where it doesn't exist. And that's a hole. Okay. So we have vertical asymptotes and holes. So vertical asymptotes, you zero out the denominator. Holes, you zero out the top and the bottom, numerator and the denominator. So let's find the points of discontinuity here. So the points of discontinuity in this first one, we again set the bottom equal to 0. which gets us, looks like x is equal to plus or minus 4. Okay, so that would be our points of discontinuity. Now if we plug a 4 into the x's on the top of this first one, a plus or minus 4, into the x at the top, we see we don't get a 0. It's still 1. We get 1 over 0. That means that we have vertical asymptotes here, or VAs. Okay, so this has vertical asymptotes at both plus or minus 4. Okay, so now let's look at the next one. So the next one, when we solve it, we get x squared plus 3 is equal to 0. That gets us an imaginary number because it gets us x squared is equal to negative 3, which isn't real. So what that means is that we don't have any point that does not exist. All reals, so there is no points of discontinuity, or PODs. Okay, so that one has no points of discontinuity because you never zero out the denominator. Now the last one, we're going to want to factor that. Two numbers multiplied together get you a negative 8, added together get you a positive 2, would be x plus 4 and x minus 2. Now since we have this, we're going to go, okay, when does that first parenthesis equal 0? That would be at negative 4. And the second one would be at 2. Now if we take those and plug of negative 4 or 2 and plug it into the x on the top, we see we don't zero them out. So that means we have vertical asymptotes again at negative 4 and 2. Okay, so this would be when x equals negative 4 and when x equals 2. We have vertical asymptotes. Okay, so let's look at this one. So if we want to describe the graph, okay, so where are vertical asymptotes, where are holes? So where do we zero out the bottom on this one? We zero out at 2 and at negative 3. Okay, so that means we have certain things there. We either have vertical asymptotes or a hole. If we plug a 2 into the top, so if we plug a 2 into here, we get a 0. That means that we have a hole at x equals 2. Now if we plug in a negative 3, we do not get a 0 on the top, which means we have a vertical asymptote when x equals negative 3. Okay. All right. And so that's what it kind of looks like. It's the same because we can reduce it through. So now if we look at the next one, if we factor the top, we'll get x minus 1, x plus 1, all over x plus 1. And as you see, those cancel, meaning that we're going to have the line of x minus 1. And we have a hole when x equals negative 1, because that's where we zero out both of those. Okay. And so that's the writing up everything. So there's a hole at x equals negative 1. Alright, now with vertical asymptotes and holes, we also have horizontal asymptotes. Well, we also have oblique / slant asymptotes, but we're not going to talk about that one in this one. But horizontal asymptotes are asymptotes, which are these lines, but this one's horizontal, so it's going along the x-axis. Okay, so it's going left to right. Now, a special thing with a horizontal asymptote is that you can cross it. Okay, you can have a point that is on the horizontal asymptote. And it's kind of like what's happening as the x values get bigger and the x values get smaller. So as it goes off into positive infinity or negative infinity, does the graph approach a certain number? Okay. Now, there's kind of like 3 rules to this. And what you're going to be looking at is you're going to be looking at the degree of the numerator and the degree of the denominator. If the degree, or the largest exponent, if the largest exponent of the numerator is larger than the largest exponent of the denominator, then there is no horizontal asymptote. Okay, so if the top's bigger than the bottom, no asymptote. If the numerator is smaller than the denominator, then it's at y equals 0. You have a horizontal asymptote and it's at y equals 0. So if the top is smaller than the bottom, you have an asymptote at y equals 0. And now the last one is what if the degrees are the same? And if the degrees are the same, you're going to take the coefficients, or the numbers out front of both of those, and you're going to do the division, the top one divided by the bottom one. And your horizontal asymptote will be at y equals the top over the bottom. Okay, we're going to see some examples of these. So you're going to be looking at the lead coefficients. So look at this first one. If we want to find the horizontal asymptote, so what we're going to be looking at is what is the largest degree. And so the largest degree on the top would be a degree of 0 because there's no x. Okay, and the degree on the bottom, since it's x, that would be x to the 1. So which one's larger, the top or the bottom? The bottom has the larger degree, okay, of 1. And so what that means is that we have a horizontal asymptote at y equals 0 because the bottom is bigger than the top. Okay. Now, if we look at the next one, the degree of the top, largest one, is 1, and the degree of the bottom is also 1. Okay. Now, since they have the same degree, we take what's called their leading coefficients. So you're going to be looking at what are the numbers that are out front of each of these variables. So this would be 1 and 1. So your horizontal asymptote for this one would be y equals 1 over 1, which is 1. Okay. So your horizontal asymptote in this case would be at y equals 1 because the degrees are equal, and then you take the coefficients out front. Going to the next one, okay. The largest degree on the top would be 3, and the largest degree on the bottom would be, did you say 2? It's not 2. It's also 3. And so we have, again, the same degree. Now, see, you're looking for the largest exponent, not the first one. You're looking for the largest. So since they're the same again, we're going to take their leading coefficients. So in this case, its leading coefficient of the top is 4, and the bottom would be negative 8. And that reduces to negative 1/2. So your horizontal asymptote for the bottom would be y equals negative 1/2. And that's where your horizontal asymptotes are. Now, if you were to graph these on your calculator, and then you make your x max really big, you'll see that they do approach those numbers. Okay. The graphs would look something like this. Top one would look something like this. And it gets closer and closer to the x-axis, because that's where it would be. Alright, so your IRAT. Your IRAT, what you're going to do is you're going to identify the vertical asymptote, the horizontal asymptotes, and the holes for each of these. Now, they might not have, if they don't have a horizontal asymptote, just say no horizontal asymptote. If they don't have vertical asymptotes, just say no vertical asymptote. If they don't have a hole, just say no hole. And so all you're going to do is you're just going to identify the vertical asymptote and the holes, which again, those are where the bottom zeroes out. Okay, that's where you'll identify those. And then the horizontal asymptote looks at which power is bigger. If the top's bigger, then there is none. If the bottom's bigger, it's 0. If they're the same, you take their leading coefficients and divide them. Okay, and so that's your IRAT. So just identify the vertical asymptotes, the horizontal asymptotes, and the holes for each of these rational functions.